All right, so let's get started. So in the last 30 minutes of today's lecture, we will announce our first hands-on. So it is about to write a system code, and later we will have TA to take over that part, and maybe there are some demo to let you know what you are going to do. So today we'll keep going on the processing interrupts. So if we have some time, we can talk about part of the memory management part. So before that, let's quickly go through some QA last time. I didn't reply it. So the first one is about if a CPU is in kernel mode, can it still serve other user process? So the answer is yes, because current CPU that are using multi-core, so kernel mode is for each core. So come to think about, if you have a CPU have 4 cores, so it is possible different cores can in different mode. And the second one is about, I think this is a little bit tough, like how does CPU handle priority inversion? So priority inversion, you will learn, and maybe if you take the real-time systems course, and this is about the real-time scheduler. And the key idea is about if there is a scenario like a high priority process is blocked by a low priority process. So this is called priority inversion. So in the real-time system, people solving priority inversion by implementing the priority inheritance protocol. So it means like if there is a high priority process blocked by a low priority process, then we just let the low priority process inherit the priority. So the low priority process will become high priority and it can quickly finish its job. So high priority process will not be blocked too long of time. Okay, but actually CFS doesn't really support the priority inheritance protocol, and I think the key reason is because CFS is not a real-time scheduler, and we'll talk about several real-time schedulers and supported in Linux. But I mean, technical-wise, if some days you are going to let CFS support the kind of priority inheritance protocol, it is still possible because it's just like a function to make an extension for CFS. So the third one is about how recalculate priority runs in O1. So actually recalculation is kind of just a way to offer an opportunity to adjust the priority. So I mean, like priority in O1 depends on a nice value. So for example, it is possible for some like system designer, if they're thinking about they're going to reassign a nice value, then in that time, we'll call that the recalculation of priority. So it doesn't really mean a very complex way to do the recalculation. I think the key thing is just like if the system administrator change the nice value, then the priority of that process will also be switched. Okay. So let me quickly do some recaps. So first of all, last time we talked about the process creation. It is a combination between a fork and an execution. So fork just to create a child by copying its parents, right? Because it is quite simple and it is efficient. And execution is quite easy, just like to load a new executable or a binary file on the memory. Okay. So because fork may take a super long time if we are going to copy all the contents from the parents. So people are saying like, hey, maybe we need a faster way. So copy on write is technology just here to solve this problem. So instead of naively copying all the resource from a parent process, we only copy the resource when the process is updated or when the new process write the data to it. So with copy on write, we can delay and prevent copying data until the data is written, and usually we will apply the read-only permission to each data. In this case, if the data is read-only, and when the data is going to be updated to be written by some new process, system can know, hey, the data is going to update, so we are going to do the copy on write. Okay. So here's just an example to show you how copy on write occurs. So last time we give a very toy kind of concept about what is a memory address. So you can think about virtual address just like the mail address, and physical address is more kind of an absolute address like latitude and longitude. Okay, so come to image like here is a memory, and then there is patch table and patch frame on it. So patch table is just like a address book that that the users or like that a process to map the virtual address to the physical address. Okay. So I'll skip this part. Just like the CPU will check the patch table and then check the patch frame. So when we are going to fork a new process, actually, at the very beginning, process 2 will not get, will not get a new copy from process 1 because process 1 and process 2 will share the patch table at the very beginning when process 1 forks process 2. So only when some of the patch table entries related to process 2, they are updated, then we will copy out the patch table. So you can see like here we say fork plus write, then we do the copy. Okay, so if there is no write, then system will not really copy a patch table for process 2. That means process 1 and process 2 will share process 1's patch table if there is no write operation. Okay. Okay. So there is another example is if we are going to update the patch frame, actually patch frame is also using copy and write. So before updating, before process 2 updates or writes the data to any patch frame, actually process 1 and process 2, they share the patch frame. Okay. So only when process 2 is going to write some data to some patch frames, that those patch frames will then be copied out. Okay. So the copy will only happen when process 2 is going to write something, when they're going to update something. In this case, system doesn't need to copy too much of data. Okay. So we also talk about the process and thread. So in Linux, actually, the definition of thread is to execute within the same program in a shared memory address space. So in Linux, it doesn't really implement thread. Oh, sorry. I think network. I think network is out. Okay. Reconnected back. Okay. So the implementation of Linux, just like the process and thread, they are all using the text structure. So the text structure, just like the PCB you learn in the operating system, and text structure is the PCB implemented in Linux systems. Okay, so threads have their own program counter, register, stack, and state. But the other things like memory, file, they are shared between each other with their own process. Okay, so Linux doesn't provide any spatial scheduling or data structure to represent threads. It means like Linux will not really differentiate process and thread and give them their own scheduler. So in the aspect of Linux, they will just do the scheduling. No matter your thread or your process, you're scheduled together. There's no dedicated scheduler for thread. Okay, so the thread creation is very similar to process creation. So the only difference is there is some tag that can be set for the thread. For example, you can set like you are going to clone the virtual memory, the file system files, and the signal handler. So those kind of things, they are shared between thread, but in terms of process, there will be an isolated version for each process. Okay. Okay, kernel threads, I think it's not important here. We talk about it. Okay, so we also talk about some scheduling things. Before talking about scheduling, we give you some idea about like priority things. So process priority, something like nice value. You can think about nice value, it is a larger value means to becomes nicer to others. So because the process being nicer, so it is usually a low priority process. And for the For lower nice value, it means like it is a higher priority process. So for most of the real-time process, they have the lower nice value. Okay, and today we will talk about what's the relationship between the real-time and nice value. Actually, it's quite simple. And then we also talk about time slice, because time slice is an important resource for CPU. Because if the CPU allocated for a process, if the process gets a larger time slice, it means most of the CPU resource are allocated to that process. So higher time slice means the process can run longer, and usually higher priority process can get longer time slice. So in some version of the scheduler in Linux, they're using static mapping. So static mapping, just like on the right-hand side, so each nice value you can get a dedicated time slice. And this is a static number. For example, you can take a look at the table, like if the nice value is 19 at the bottom of the table, then the time slice will be 5 milliseconds. Okay, so if the nice value is -20, that means the time slice is 800 milliseconds. So actually, if you open up like Linux, an older version of Linux kernel, like before, I think 4.4, something like that, you can find this kind of table and this kind of mapping. For example, which nice value can be allocated how much of time slice. So this is also adjustable. I mean, if you are going to define your own mapping between nice value and time slice, it is also doable. Okay, so we point out 2 challenges for this static mapping. The first one is, in terms of low priority process, I mean, if in some kind of timing in the system, most of the process there are low priority, then those processes will trigger context switch super frequent. Because take a look at this table, like if low priority process, they only get nice value 19, for example, then for each low priority process, they will switch for every 5 milliseconds. So doing context switch too frequent, you will consume a lot of CPU resource. So this is the first challenge. And the second challenge is a time slice difference. So take a look at nice value 19 and 18. Actually, nice value 18, the process can get twice the time slice of nice value kind of 19's process. But when we focus on nice value -19 and -20, that is high priority process. Actually, the difference is quite small, like 790 milliseconds and 800. 780 milliseconds and 800. Actually, the difference is only 20 milliseconds. And 20 milliseconds divided by 800. Actually, it is only 1/40. It is a very tiny difference between high priority process. So it is unfair for low priority process. So how to deal with these 2 challenges? Actually, last week we talked about a CFS. Okay. So we go through 2 I would say like 2 outdated scheduler for Linux. The first one is ON and the second one is O1. So ON is quite simple, just like it maintains a shared global run queue. So each time when we are going to reschedule, then CPU needs to enter the run queue and pick the one that needs the CPU resource most. So how to pick the one needs the CPU most actually depends on their time slice. It depends on the nice value. So you can think about in the global run queue, CPU will first do the sorting, and then they can get the one that needs the CPU most. And then because this is a global resource, so actually when there is one CPU is going to access this global run queue, it needs to lock the run queue, right? Otherwise, other CPU will modify it. So to avoid this kind of synchronization issue, global run queue should have their lock, but using lock will lead to bad performance because when one CPU is in, the other CPUs cannot use it. Okay, so performance is one issue for the ON. And if we are going to make it faster, actually, we need to get rid of this global run queue. So for O1, actually, we maintain several run queue. What do I mean several run queue? If you still remember, actually, there is a 140 bit maps, right? So for each bit value means if there is a ready process in the queue, So not only 140 bits map, we also maintain a 140 run queues. Then each run queue means one priority. So in this case, we can alleviate the overhead to go through this global run queue. Just like we break the global run queue to 140 smaller run queue. Okay. So this strategy is going to set like if there is one process that is added to the system, and we will first check what is the priority of that process. So for example, if the nice value is kind of I think this is kind of from 1 to 140, sorry, for 0 to 139, for example. So if the nice value is 1, for example, then the bit will be set, and then the process will be added to the Q1. Okay. So if there is one process in the queue, then the bit will be set. No matter how many other processes will be added into this queue, if there's one process in the queue, at least one process in the queue, then the bit will be set. So this bit can be indicated if there is any process in that queue. Okay. So CPU will use some spatial instruction to find the leftmost bit set in this bit array. The reason to find the leftmost bits is because the leftmost means the higher priority. Okay, so here is higher priority and this is lower priority. So if we are going to get one process that needs to be scheduled, then we should pick the one as a higher priority, right? So at this time, we will pick the one from the leftmost in this bit array. And then after picking it, after getting the index, for example, in this case, is 1, then we will go to check the Q1. And then for the Q1, if there are several processes inside this queue, then we will use the FIFO to maintain it. Okay, so FIFO means like first in, first out. So if there is a process added, just like a FIFO queue, then we will pick the first one that enter the queue. Okay, so after running that process, for example, if the process use up all the time slice, then we will maintain another same data structure, but that is not for a ready process, that are for expired process. So you can think about we have another expired bit array. It is also 140 bits. And then we have a set of the same 140 queues. They are all for the expired process. Okay. So we will do the recalculation priority. So it depends. For example, for some system manager, they will think like if one process use up all the time slice, then probably they are going to lower the nice value, for example. So when the nice value is changed, we need to recalculate the place for that process. But if the nice value doesn't change, then we don't need to do the recalculation. Okay, so recalculation is related to the nice value. Okay, so until one day, if there is no bit is set in the active bit array, it means most of the process they are served and they are added to the expired bit array. Then we will directly switch the data structure. So what I mean switch is originally if this is for active process and this is for active array, and we will switch it. So we will directly assign this becomes expire and expire. So the expired bit array and expired queues will be virtually set as the running. Okay. So in this case, we don't need too much of overhead. We just switch the bit there. Okay. So this is the ON and O1. And the bad things for O1 is because actually this scheduler doesn't really care too much of low priority process, because if you are low priority process, in most cases you need to wait to a very long time, because most of the high priority process should be finished. Then you can execute the low priority process, right? And then if you still remember, even now O1 it is using nice value, and then it is a static mapping. So for high priority process, it will occupy a super long time on CPU. That means low priority process cannot get too much of CPU time. Okay, so CFS is going to deal with this problem. CFS is going to make low priority process can also be interactive, can also get enough time slice. Not much, but just enough. Okay. So CFS, just like it was used after kernel 2.62, I think is 4 point something late. So it was used for a super long time. So there are two main concepts for CFS. The first one is instead of statically mapping time slice, each process would receive 1/n of the processor time. So because because there is a processor time, for example, if we set the processor time as like 1 milliseconds, then if you have 10 process, then the 10 process should be sure to list 1 milliseconds. So no process can use like more than this 1 milliseconds, this kind of time. Okay. So this is very different from static mapping because it means for each process, it needs to also consider how many processes are scheduled in the same time. If there are more processes, then the time slice for each process will be fewer. Okay. So the other concept is to schedule process for infinite small durations. So infinity small duration is just to make it more fair because here the process each process can only get 1/n of the processor time. So if this processor time becomes super small, then each process can feel like it can be served in any time. Okay. So this is the key concept of the CFS. So we talk about if we are going to implement these kind of things, actually we need the things called virtual runtime. So virtual runtime means the combination between the real system runtime plus the priority. Okay, so higher priority, you can get a little bit longer time slice, and lower priority, you should get fewer time slice. But overall, if you have m process, the overall time slice that summarized together, they cannot be exceed some threshold. Okay, so theoretically, virtual runtime, the calculation for virtual runtime is like delta execution times nice weight over nice k weight. So nice k weights here is the k process they are scheduled now, and the nice weight is the process that the process get. Okay, and delta execution is the period to enter scheduler. So delta execution means the processor time here. Okay, so process times means delta executions. So each process can get 1/n, and 1/n just precisely calculated by this nice dash weight over nice dash k dash weight. Okay. And vertical, we already talked about it just because the floating point part. And after the calculation, actually each process can get their virtual runtime, right? So in order to get like which process should be scheduled earlier, we use the red black tree because red black tree can control the tree height. Okay, so virtual runtime will becomes the index for each node. So we use the virtual runtimes. We use the red black tree to quickly get the process that are going to be scheduled next. So the time to traverse the tree is log n. So this is the reason why CFS, the complexity of CFS is log n, because if we are going to get where the next to be scheduled data is. So each time we will get the lowest virtual runtime in this tree. So lowest virtual runtime means the most need of CPU, and larger means the least need of CPU, just like these kind of things. Okay. Okay. So one thing to keep in mind, actually CFS is not faster than O1 because O1 really the complexity is O1. But CFS we need log n because we need a red black tree to help to know where is the to be scheduled process is. Okay. So we also talk about how to decide this part because this part is the main part about the CFS, right? So okay, so how to decide the weight? Because we are saying like we don't want it becomes too static, and then we don't want to map the sorry, let me go back. Okay. Okay. We don't want like challenge to occurs, just like low priority process usually becomes unfair. So we need a way to like normalize this kind of time slice. And in Linux, like they are using this kind of 10% effect. So there are some calculation here. Okay. So after some calculation, you can get like, for example, if your nice value like 20, you can get 15 milliseconds. And then if you're 19, then you can get 18 milliseconds. But after the calculation, actually, no matter which time slice no matter which nice value you are, you will be only 10% larger or smaller than your neighbors. Okay, so the gap here, usually there are around 10%. So there is no fairness issues in this scenario. Okay, so let us know about last week. So today, let's start from real-time scheduling policies. So I will just only touch very a little about the real-time scheduler, because if you are interested in, there is a course like real-time scheduling. So there are two different kind of real-time process: soft real-time and hard real-time. So soft real-time means the kernel tries to schedule applications within time deadlines. So it means soft real-time process can violate their timing deadline. Okay, but hard real-time process cannot. Just like systems are guaranteed to meet any scheduling requirements within certain limits. Okay, so hard real-time means like if there's one process, say I need to finish it in like 1 milliseconds, then the system should not fail that process. Okay, the system should allocate enough resource to that process. So in Linux real-time scheduling policies, actually the priority range is between 0 and 139. So this is the reason why when we are talking about O1, there are 140. Because 0 to 139, there are 140 priority levels here. So from 0 to 99, they are for real-time process. And 100 to 139, they are for normal process. Okay, so actually most of the kernel process, like kernel function, there are real-time process usually. Okay, and normal process just like the user process. Okay, so there are several ways to do the scheduling. The first one is FIFO. So FIFO means tasks continue to run until it blocks or explicitly yields the processor. So actually FIFO means there is no time slice. Okay, so the time slice in FIFO it doesn't have. So just like first in, first out. So if you are a high priority process, you can occupy the CPU resource for a super long time. Okay, until if there is another higher priority process and they can preempt the prior one with the lower priority one. Otherwise, you can run a super long time because there's no time slice. So only a higher priority FIFO queue process can preempt it. Okay. So there is another kind of scheduler called round robin. So in round robin in Linux is a FIFO with time slice. So round robin, I think you already learned in all operating systems, just like each process will periodically get the resource, right? And for this version of round robin, you can think about it's a FIFO with time slice. So for a process using FIFO, they'll get a time slice, and if they use up their time slice, they will release their CPU resource. Okay, but there is still some constraint, just like a lower priority process can never preempt a round robin task. Okay. So that is the real-time scheduling for this course. Just like to let you know, actually in Linux, there are FIFO and RR. But usually when you are running the user process, actually you are using CFS. So not the RR or FIFO. RR and FIFO, they are used for the real-time process. Okay, so that is the things in Linux. Okay, so we talk about like scheduling, and when you are doing the scheduling, there is a things called reschedule. Just like you are going to schedule another process and you are going to stop the current process, right? But the current process, they are still using CPU resource. And how to schedule another process, and this is called a process context switch. So usually in the textbook, people call them context switch. And the reason I'm going to add process here is because when the CPU is going to switch from user mode into kernel mode, there is also things like context switch, and I'll explain it later. Okay, so process context switch, like we need to first define what is the process context. Okay, so process context just like the content of user address space, hardware register, and kernel data structure that relate to the process. Okay, so I think it is quite hard to understand what it is. So I'm trying to use some example. So it's just like you can think about like this. Context is very similar to an environment to run something. So process context is just like an environment to run a process. What do you need? For example, you need the user address space because you need a patch table to find the data. So this is environment for the process. And not only the user address space, you also need some hardware register, some program counter, some register there. There are a lot of registers that are related to a process, and you need all those kind of register, right? You need to kind of checkpoint the register state, and also the kernel data structures. So like the kernel stack, those kind of things. Okay, so those are all related to the process context. Okay, so process context switch is quite simple, just like switching from one runnable process to another. But how to implement it is very complex. And there are two main steps for process context usually. The first one is called the switch-mm. I mean, those are all in Linux function. So switch-mm means to switch the virtual memory mapping. Because when we are saying we are going to switch from one process to another process, means we are going to run another process, right? And for Linux and for most of the operating systems, each process has their own patch table. So if we're going to switch a process, means we need to switch a patch table. Okay, so there are several things related to a patch table, like the patch table and then TOB, MMU, those kind of things. Okay, and not only to switch MM, but also switch to. So the switch to function in Linux means to switch the process state. So including the processor, register, architecture, specific stack, all those kind of things. Okay. So I think switch-mm is quite not that complex. So I will first talk about it. So when we are going to switch the memory mapping, the first thing is to flush the branch predictor buffer. So branch prediction, I think maybe you learn in the architecture, but if not, it's still no worries. Just like branch predictor is just about if we are going to run some program, and if there is a branch occurs, for example, if there's an if else, then if you go for example, if or else, actually you can do some guessing about how many percentage the program will go for if and how many percentage will go for else. So if you think like go for if is higher priority, for example, it is 70% you will go for if, then you can try to execute this kind of if condition more. Otherwise, if you think like the false condition there's 30%, then you can just make 30% of the process in the false condition. So just like you are going to pre-execute something there. And then when you are going to do this kind of branch prediction, actually you need some register for that process, right? Because they will be depending on their code. How does their code look like? So you need some register to do the recording things. So another thing is about you need to load new patch table, right? So in Linux, actually, the patch table is controlled by a register called CR3. So CR3 register will point to the root for the patch table. And we will talk about the patch table later. So you will know how CR3 function in working the patch table. And then after it, CPU should flush a TOB. So TOB works like a cache for caching the patch table entry, right? So if you still remember, we say the virtual address and physical address, just like the mail address and the absolute address. So we need some mapping there. We need some address group to map it. And TOB is something that can help you to cache it. So if we already do the translation, why not just cache in our CPU? So TOB you can think about it's just like a very tiny SRAM and it is possible to cache part of the translation results. Okay, but if you are going to switch from one process to another process, definitely the next process doesn't need the TOB result because they have their own patch table, so the TOB should be flush. Okay, and then there are also some kind of register related to the paging, for example, CR4. So CR4 is more like the page size extension. So for example, if you are going to use a larger page size, but I think this is not really important in this class because I mean, it depends on the CPU architecture and this is just a function for the CPU. Okay, so in the prior version, you're going to load LDT, those kind of descriptor table, but it really depends on which kind of processor you are using now. So in current new CPU, you don't need this step. Okay, so here just to let you know, actually, if you are going to switch the virtual memory mapping, actually you need to do a lot of things. Okay, but don't worry. I mean, in the exam, I will not ask you to draw this out. Okay. So switch to is more complex because there are more kind of things related to the process step. Okay. So at the very beginning is to push the register to Ceph because we are going to switch from one process to another process. So if you still remember, we say a process means the program and all the runnable resource, right? The CPU resource, memory resource that we are using. So we need to store most of the CPU register in case we are going to switch back. We can quickly resume the process. Okay. And then there are several things. First one is we need to solve the stacks. Like each process has their user stacks, right? And kernel stacks. So we need to solve the stacks. And then we need to set the floating point unit because floating point unit is a hardware in the CPU and it maintains the floating point computation resource. So we need to set the floating point unit resource for each process. Okay, so ring zero stack is just like a kernel stack. Okay, so there's also things called save and load, the data segment and programmer defined segment. So data segment, it is a little bit look like if you already learned the undergraduate operating system, it is like BSS segment, it is in the data segment. So BSS segment is just like when you write a program, you say, I'm going to say like to define an integer, int, and there's an x, right? So this program, they owns their own int_i, these kind of things. And those kind of informations, they will be saved in this data segment. So you can think about just like the parameter initialization things. And those of the information will be in the data segments. And programmer defined segment, you can think about just like a map. So in your code, if you say you are going to map a region of memory, and those kind of information will be put in this kind of programmer defined segment. Okay, and those kind of segments, they are all on demand. So only when you need this kind of resource, those kind of information will be moved from the memory to the CPU. Okay, so those kind of information is just about if you use those kind of information and they are now in the CPU, we need to do a backup. We need to write them back to the memory. Okay. Okay. So update thread local storage. Okay. Actually, this is kind of tricky things because thread local storage, you can think about just like each thread can define their own parameters. Okay. So when you're writing a program, when you're writing a P thread, and each P thread can define your own parameters, and you can choose not to switch between other P threads. Okay, so each user thread can have their own private parameters, and those kind of private things, they will be put in this kind of thread local storage. Okay, and okay, let me take a look. Okay, so FS and GF you can think about because this thread local storage is an area, so you need a register to point to that area. So you need to save and load where the thread local storage area starts from. So this is about the FS and GS register they are used for. Okay, so I think there are most of them just like PDA, context is just like those kind of IRQ. IRQ we will explain later. It is about the interrupt handler things and MMU step. Those kind of things, they are all processor related information. They will all need to be switched out. Okay, so there are several kind of notes here to let you know what is it about. But don't worry, the same things I will not ask you about to draw this out, and even I will not ask you about what is FS in the exam. So this figure is just to let you know, actually, when you are going to run process context switch, it is very complex here. And if you notice, like this figure is from like Linux kernel 2.6. So actually, if you get the Linux kernel like 4.4 or like 5 point something else, you'll get a more complex one, because in 2.6, the virtualization technology is not supported that well in CPU. But in 4.4 or like the later version of the kernel, there are kind of mature virtualization, and you need to do more things to store this kind of virtualization state. Okay, so this context switch will become more complex. So this is also the reason at prior slides we say if you are using O1 scheduler and there are kind of a lot of low priority process, you need to do the context switch so frequent. Maybe you'll think like context switch is so fast, why we need to care about it? But actually, context switch takes a lot of time. For example, context switch usually take 1 to 10 microseconds to run it. So you can think about 1 to 10 microseconds. Maybe you feel like it's not very long, but one instruction only needs usually only needs 0 point something nanoseconds. So 10 microseconds means you can run more than 10,000 of instructions just to finish one context switch. So it really takes times. Okay. Okay, so check. Okay, so because I always highlight about mode switch and context switch things, so in this slide, let me briefly summarize CPU mode switching and what does really matters to put these two things together. Because in most cases in the undergraduate, we only learn about the process context switch and we call them context switch. But actually, the concept of context switch is to switch to, I would say, like informations. So information including the CPU information, memory information, and file information. So come to think about one question. If we are going to do the CPU mode switching, we are going to switch from user mode to kernel mode, right? But actually, a user process, there are the kernel space purely for user process. And for that user process, the higher 1 GB there for kernel process, right? So for each user process, you have 2 kernel space, one for user address and the other for kernel address. So when you are going to do the mode switching, actually, you also need to switch some register in the CPU. Okay, so this is the reason doing CPU mode switching is a little bit similar to process context switch, but process context switch need to do more things because we need to aware of more kind of memory, file, those kind of information, but mode switching doesn't. Okay, so CPU mode switching occurs just like some exceptions or interrupts happen. So CPU will switch from user mode to kernel mode to run the kernel code, right? Okay, so CPU should also do context switching, but not process level context switching. So the reason is like before switching to kernel mode, CPU should save user mode context. For example, when we are going to jump from the user process to the kernel function, the thing is, how about our program counter? How about our register to run this kind of program counter? Because you are going to switch to different code, right? Linux kernel just like a full program, and your user program is another program. When you are going to jump from one program to another program, you need to switch the register. And each register you can think about, it is a part of the context. So including program counter, user mode specific stat, for example, user space stack pointer register, those kind of register, floating point register, user space instruction pointer, they are all needed to be set when you are doing a mode context switch. Okay, but this is quite simple because I mean, process context switch, as you already saw, there are a lot more than this kind of information here. Okay. So I think there is an interesting thing here. When we say save context, we generally mean to write back all these registers to the corresponding process descriptor in main memory. Okay, because if you still remember, each PCB or each process descriptor means most of the information related to this process, right? So those kind of information is just like a metadata. They are all in the main memory. And then when CPU run this process, CPU will load this kind of process descriptor to the register, so CPU can start to run it. But when one day you are going to stop this process, and then there are some status, right? Because for example, which part of the program the process is running now. So we need to store this kind of register back to the memory, and we need to fill in this kind of text structure. Okay, so there are some mapping between the process descriptor and the register inside the CPU. Okay, I think this is quite important. Just like context switch is, we need to store the information from CPU back to memory. So this is another reason that it takes a little bit long time, because not only to run something inside CPU, it needs to move some information back to the main memory. And writing main memory takes longer time than purely CPU execution. Okay, so that is about it. And then let's move on to system code part, because your hands-on today will be related to system code. So let's briefly talk about what is system code. Okay, so actually the goal for system code you can think about is to let user-space process interact with the operating system. So the kernel provides a set of interface, and that interface, they are called system calls. Okay, so here is just an example. I mean, there is this, I think, I'm not quite sure can you guys see, but this is kind of a snapshot from the Linux kernel. So actually the system code look like these kind of things. Like there are some definition of the system code number, and then what kind of system code it is, a read or write system code, and where the process is. I mean, these kind of things, they will be linked to the place, the address of the starting point of that system code. Okay. So how to run a system code? System codes are accessed via function codes defined in the C library. So just like this, for example, if you are going to show something on your screen monitor, so it just looks like you are going to write something on your screen, right? And in Linux, actually, there doesn't really have a screen. I mean, there is a file, for example, there is called TTY file for the screen. So when you write something in that TTY file, Linux will show the things you write on the screen. Okay, so if you are going to write something or you are going to show something on the screen, actually, there's things called the printf function. Okay, so printf in C library, actually, you can find it in there is a if you trace back to the C library, you can find this kind of things called write in the C library. Okay, so write actually means they will call the system code. Okay, so library will help you to wrap up most of the things you don't really need. For example, in the user level, you only need to know when you are going to show something on the screen, it is a printf function. But at a lower level, the C library will help you hook with the function system code function in the library. Okay, so there is a very tricky thing is each system call has their own unique number. So for example, in this example, you can see the read here means system code 0 and write means system code 1. So when you are writing your program, actually, if you open up the system code table, you can see there are a lot of, I think it's kind of 500 or like more than 500 of system codes there. So if you are going to add your own, you can find a unique number they are not used now. Then you just register it and you can get a system code. Okay, so system code table is just like the kernel keeps a list of all system codes in this table. So actually this information we capture it from the system code table in this latest version. Okay, so I think let's take a 10 and then come back later.